You write that the phenomenon of emergence, collective behavior exhibited by a large collection of simple elements in interaction, is one of the things that got you into neural nets in the first place. I love cellular automata. I love simple interacting elements and the things that emerge from them. Do you think we understand how complex systems can emerge from such simple components that interact simply?
No, we don't. It's a big mystery. Also, it's a mystery for physicists. It's a mystery for biologists. How is it that the universe around us seems to be increasing in complexity and not decreasing? I mean, that is a kind of curious property of physics, that despite the second law of thermodynamics, we seem to be, evolution and learning and etc. seems to be kind of, at least locally, to increase complexity, not decrease it. So perhaps the ultimate purpose of the universe is to just get more complex.
Have these, small pockets of beautiful complexity. Do cellular automata, do these kinds of emergence and complex systems give you some intuition or guide your understanding of machine learning systems, of neural networks and so on? Or are these for you right now disparate concepts?
Well, it got me into it. I discovered the existence of the perceptron when I was a college student, by reading a book on, it was a debate between Chomsky and Piaget, and Seymour Papert from MIT was kind of singing the praise of the perceptron in that book. And I the first time I heard about the learning machine, right? So I started digging the literature, and I found those books, which were basically transcription of workshops or conferences from the 50s and 60s about self-organizing systems. Mm-hmm. So there was a series of conferences on self-organizing systems, and these books on this. Some of them are, you can actually get them at the Internet Archive, the digital version. And there are fascinating articles in there there's a guy whose name has been largely forgotten, Heinz von Förster. He's a German physicist who immigrated to the US and worked on self-organizing systems in the 50s. And in the 60s, he created, at University of Illinois Urbana-Champaign, he created the Biological Computer Laboratory, BCL, which was all about neural nets. Unfortunately, that was kind of towards the end of the popularity of neural nets, so that lab never kind of strived very much. But he wrote a bunch of papers about self-organization and about the mystery of self-organization. An example he has is, imagine you are in space, there's no gravity. You have a big box with magnets in it, okay? Kind of rectangular magnets with North Pole on one end, South Pole on the other end. You shake the box gently, and the magnets will kind of stick to themselves and probably form complex structure, spontaneously. That could be an example of self-organization. But, you have lots of examples. Neural nets are an example of self-organization in many respects. And it's a bit of a mystery, how, what is possible with this? Pattern formation in physical systems, in chaotic system, and things like that. The emergence of life, things like that. So, how does that happen? It's a big puzzle for physicists as well.
It feels like understanding the mathematics of emergence in some constrained situations might help us create intelligence, help us add a little spice to the systems, because you seem to be able to, in complex systems with emergence, to be able to get a lot from little. And so that seems like a shortcut to get big leaps in performance. But
there's a missing theoretical concept that we don't have.
Yeah.
And it's something also I've been fascinated by since my undergrad days. And it's how you measure complexity. Right. So we don't actually have good ways of measuring, or at least we don't have good ways of interpreting the measures that we have at our disposal. How do we measure the complexity of something, right? So there's all those things, Kolmogorov-Chaitin, Solomonov complexity of, the length of the shortest program that would generate a bit string can be thought of as the complexity of that bit string, right? Mm-hmm. I've been fascinated by that concept. The problem with that is that that complexity is defined up to a constant, which can be very large.
Right.
There are similar concepts that are derived from Bayesian probability theory, where the complexity of something is the negative log of its probability, essentially, right? And you have a complete equivalence between the two things. And there you would think, the probability is something that's well defined mathematically, which means complexity is well defined. But it's not true. You need to have a model of the distribution. You may need to have a prior if you're doing Bayesian inference. And the prior plays the same role as the choice of the computer with which you measure Kolmogorov complexity. And so every measure of complexity we have has some arbitrariness in it. An additive constant, which can be arbitrarily large. And so, how can we come up with a good theory of how things become more complex if we don't have a good measure of complexity?
Yeah, which we need for this. One way that people study this in the space of biology, the people that study the origin of life or try to recreate the life in the laboratory. And the more interesting one is the alien one, is when we go to other planets, how do we recognize that it's life? Because, complexity, we associate complexity, maybe some level of mobility with life. We have to be able to have concrete algorithms for measuring the level of complexity we see in order to know the difference between life and non-life.
And the problem is that complexity is in the eye of the beholder. So let me give you an example. If I give you an image of the MNIST digits, right, and I flip through MNIST digits, there is obviously some structure to it because local structure, neighboring pixels are correlated across the entire data set. Now imagine that I apply a random permutation to all the pixels, a fixed random permutation. Now I show you those images. They will look, really disorganized to you, more complex. In fact, they're not more complex in absolute terms. They're exactly the same as originally, right? And if you knew what the permutation was, you could undo the permutation. Now, imagine I give you special glasses that undo that permutation. Now, all of a sudden, what looked complicated becomes simple.
Right.
So if you have humans on one end, and then another race of aliens that sees the universe with permutation glasses.
Yeah, with the permutation glasses.
Okay. What we perceive as simple to them is horribly complicated. It's probably heat.
Yeah, heat, yeah.
Okay, and what they perceive as simple to us is random fluctuation. It's heat.
Yeah.
So
truly in the eye of the beholder. It depends what kind of glasses you're wearing.
Right.
Depends what kind of algorithm you're running in your perception system.
So I don't think we'll have a theory of intelligence, self-organization, evolution, things like that, until we have a good handle on a notion of complexity, which we know is in the eye of the beholder.
Yeah, it's sad to think that we might not be able to detect or interact with alien species because we're wearing different glasses.
Because their notion of locality might be different from ours.
Yeah, exactly.
This actually connects with fascinating questions in physics at the moment, like modern physics, quantum physics, questions about can we recover the information that's lost in a black hole and things like this, right? And that relies on notions of complexity, which I find this fascinating.